We learned that when you have an object that's that's moving from point A to point B with a velocity, it carries energy. What kind of energy is that when it's moving? Huh? Kinetic energy, right? So it has kinetic energy, and that kinetic energy is equal to 1/2 mv squared that we know. So when you have an object moving with a velocity, it has kinetic energy that's 1/2 mv squared. What about when you have something that's rotating? It is rotating, it is moving, it has a velocity. We just showed that the velocity is related to angular velocity, right? So there is a velocity. So what is the energy associated with this, kinetic energy? Sorry, I should say that. So, there should be a kinetic energy associated with this motion, right? Because it is moving. So our task here now is that how do we find the kinetic energy, well, for rotating object, okay? So now let's look at this object again. So this object basically consists of many different particles. Let's say if we just divide this object into small particles, and each is moving up, about this central axis. So every part of this object is moving, along this, around this central axis. So each part of this particle has its own velocity. Whenever it has its own velocity, we can take a small amount of that piece. So we have the velocity, we have the mass, and you sum up all the terms, 1/2 mv squared. Then that will give you the energy of this rotating body, right? That makes sense because you just take a small amount and say, okay, this is the mass. Instead of taking it as a whole piece, this is a tiny little mass. It's moving at this velocity, and at this part it has this mass. So in other words, you kind of divide this portion into small parts, and you integrate that, and you sum up all the small all the contribution from each component to find your total velocity. So basically, to find the energy of that rotating object, we can do that. Based on this, we can say that the kinetic energy is, let's say, 1/2 n1 v1 squared, 1/2 n2 v2 squared, blah blah blah. So you just you divide this, extend the object into small parts. Each part has its own velocity. You just apply this equation, and then sum up all the possible, all the contribution. So in terms of math, you can say that it's summations of 1/2 mi vi squared, and that of course is depends on how many parts that you sum it up. Okay, so in that case, we have 1/2 mi vi squared. Now remember, so this is when this is when we find the kinetic energy based on our concept. Based on our knowledge on the object that's moving with the velocity v, okay? Let's say when you have an object that's moving with the velocity v, you can use 1/2 mv squared. And basically, we're just using, okay, for a rotating body, we're just taking, okay, this object has a velocity v, this object has a velocity v. We're just treating it as a different object, and then sum up all the contribution. Yes. Oh, this one? This is summation.
And what's above it? Is that an n?
That is your that's your I. I'm sorry. So this is subscript I. So depending on how many parts, right? And then so 1, 2, 3. That's 100 or 200. Doesn't matter. So it's just a dummy variable. Okay. All right. So this is, we obtain the expression for kinetic energy when you utilize the concept that you learned for linear motion. So you have this. Now let's see what we can do with this equation. We already know that when you have an object that's moving, or is rotating, it is related to the linear velocity. How are they related to each other? So in other words, v and omega, how are they related to each other? V is equal to R omega, right? So in that case, now we're going to utilize that relation, okay? That relation, and then replace our V with that expression to see what we get. So your K here is equal to, so you have summation, and then you have 1/2, and then you have mass does not change. And your V now is equal to your R, and then you have your omega. So you have your Ri omega, and then square it. So you might wonder, okay, so the subscript here indicate that, you have your I here and then I here. What happened to the omega? Why is an omega having an I, the subscript? And that's because we're assuming that every part of the object have the same angular velocity. So the same angular velocity does not change. The only thing that would change, the only thing that changes is the radius, how far away from the central axis, and that determines the magnitude of the linear velocity, right? As I mentioned, this is the radius. So if the object is located here and the object is located there, I mean, they will have a different velocity because the radius will be different. Okay, so that's why when you have a rotating object with the same angular velocity, then linear velocity and angular velocity, they are related by this, and the only thing that would change is just the radius, how far away from the rotation axis. So what we have here is that your kinetic energy now can be represented by the angular velocity. So let's rearrange this. What we have here is summation, and then you have your 1/2, and you have individual mass, and then Ri, your R is squared, this whole thing, and then times omega squared. Now let's look at this. Let's compare this and this. They look very similar to each other. They all have 1/2. They have mass I, but then this is the mass I times the radius squared. And then you have the V squared, you have the omega squared. So remember, we've been comparing the linear motion and rotation to see what would be the equivalent counterpart in rotation. And we identified that V and omega is the counterpart of V in rotation. What about this, the mass? The mass also has a counterpart. Okay, so in linear motion, if you consider that as a mass, in rotation, instead of using mass, we have this new quantity, which we call that I. Okay, and that I is what we call rotation inertia. Rotational inertia. And we use capital I to indicate that's rotation inertia, which is equivalent to mass when you're dealing with linear motion. Your I here is the mass in rotation. So this is equal to summation, and then you have your 1/2, and then you have your, let me see. So let me just write here. So your I here is a summation, mass, and then Ri squared. Okay, so in that case, what we have here is that we're going to replace this summation of mass times Ri squared with I. So what you have here is that's 1/2 I omega squared. So when you have an object that is rotating, how would you find the kinetic energy? This is how you calculate the kinetic energy. That would just be 1/2 rotation inertia and then times omega squared. Okay, and omega is the angular velocity. Any questions so far? Why are we doing this? Because if you remember, for a single particle, your K is equal to 1/2 mv squared. You can see there's a direct comparison between this and this. So instead of 1/2 mv squared, you have 1/2 I omega squared. Okay, and your I, how do we calculate I? Your I here is defined as the summation of mass times the radius squared. And you use a subscript I to indicate because there might be different components within consist of that makes up the object. Okay. All right. So this is basically how would this is in pure rotation. When you have an object that's in pure rotation, that the kinetic energy is 1/2 I omega squared. When you have an object that's in pure linear motion, this is in pure, instead of linear motion, we call that translation. Okay. So this is the difference, similarities and differences between those two. Okay. All right. So This is when you have an object that is divisible. What about when you have a continuous object? Then you cannot just directly sum up all the points. You have to use calculus. So in that case, when you have to use calculus, this is expression, which of course will not go into detail. But this is basically how you find the rotation inertia when you have an extending object. When it's not, you cannot divide it into like tiny little portion. You have to use calculus to calculate your I. Okay. All right. So you can see that when you have an object that's rotating, it's very easy just to calculate, use this equation. So you have k, that's 1/2 I omega squared. And I, of course, is a rotation inertia, which is mi squared. So for every object that's rotating, all you need to do, if you, rotation, the angular velocity is very easy to find. But what about rotation inertia? For this object, what would be the rotation inertia? That would not be that simple. But then, for the cases that you're going to encounter, we pretty much know the rotation inertia, so you don't have to worry about that. Okay. Now, before I show example of the rotation inertia for different objects, because different objects will have a different rotation inertia, I just want to mention that there's an important theorem. So let me just talk about that important theorem before I show you the rotation inertia for different objects. There's an important theorem that is called the parallel axis theorem. What it says is that, let's say, if you have an object that's rotating about the central mass, most of the time when you have a rotating object, that object is extended body. So you have to find out what is the central mass of that object. And then let's say if you have a rotation that's not through the central mass, how would you find the rotation inertia about a new axis? Okay. So take for example, you have a stick. And let's say this is a side view. You have a stick, and I'm going to let it rotate. So we can rotate like that, right? And let's say it is rotating about this axis. So it's rotating like this. Okay, and so this point, because this rod is, let's say, is uniform. So the central mass will be at the center of this rod. So it's rotating like that. So you have what we call the ICOM, which is basically rotation inertia through the central mass. Usually they are very easy to calculate. And then what about when you have a rotate? If you're not rotating, if you rotate this bar not against this, the central axis, instead, I'm going to actually let it rotate through this endpoint. So this is your new rotation axis. So the whole thing here is going to rotate about this new axis. What will be the new rotation inertia? That would not be the same as that one. Because if you remember, your I here depends on the radius. So in this case, the radius, this is your radius. But then in this case, this is your radius. The radius would change. When the radius changes, it means that rotation inertia will be different. And so let me just ask you. So which one do you think will be easier to rotate? Through a central mass or through this axis? Which one will be easier for this to rotate? Yes? Center mass, right? Why? Because by using parallel axis theorem, you'll find that your I here is always greater than the central mass, the rotation, the I of COM. So that's why when you have, so I of COM is actually smaller. When I is smaller, if you remember your K here is 1/2 I omega squared. So if this is smaller, which means that you require smaller energy, so it's easier to rotate. Okay. Now, why did I say that this I will always be greater than ICOM? ICOM is central mass. This is where when you rotate through a central mass, is the energy required is smaller than when they rotate through any different other axis. So let's see parallel axis theorem. What does that tell us? It tells us that if you're rotating about a different axis other than the central mass, your rotational inertia has to be modified. And how is it going to be modified? It's basically followed by this equation. So the new rotational inertia is equal to rotational inertia through the central mass, and then plus whatever the vertical distance between them. So I'm going to call this as L, the distance between the new axis and the axis through the central mass. And then the mass of this object. That's called M. Okay? So you have M and then L squared. So you can see that the center mass is always win because it is, your new rotational inertia is always this plus this term, and this term is always positive. So rotational inertia through the central mass will be the smallest compared to all the other rotational inertia. That's why when you're rotating through the central mass, then it will be the easiest than rotation through any other axis, because the energy requirement for this is much smaller than the energy for rotating through other axes. Okay, so in other words, ICOM usually will be given. Sometimes it is not rotating through the central mass. Then you have to use this equation to calculate the new rotational inertia, and then it is the mass of the object and then times the vertical separation between the two objects. So when I say vertical separation, what is the distance between them? That's what we call the vertical separation. That will be your L here. Or you can have a new axis, let's say right here. So in that case, this is the distance, and you still have your M here. Okay, so you can see that when it closer to the central mass, the easier you'll be for you to rotate the objects. Okay. Okay, so now I'm going to show you what are the usual things that we learned for the rotational inertia through the central mass. Let me see this. Is that right? Do I use that? So I'm just going to project it to the screen and. Yeah. Yes. What is that? Okay. Let's see. Now it's a 70, so 70, that's 78. What?
Lab groups right here. Power.
All right. Is it clear for you to see, or do I need to bring down the screen? Okay, so can somebody that's taller that can reach that rope to bring down the screen? Dan? Thank you. I'll have you sign the media release waiver form. Okay. All right, good. And I think I probably have to turn off the lights just to make it. Is it better? It is. I don't know. Let me see. I should use the full screen. Okay, let me see. Slideshow. Current slide. Oops. All right. Now you can see that what this table shows is that for different objects, to calculate the rotational inertia will be different. So you don't have to write down the formula for that, because when I ask you to do problems and find the rotational inertia, then those expressions will be given. But when you do problems on your own, you have to look up to this table to see what is the expression for the rotational inertia through the central mass. For example, this is a solid sphere. This is so fuzzy. I can't even tell what is this. It's 2/5. I think it's 2/5. Yeah. So you have the rotation through the through this. So this is what we call the rotation through this through the diameter. So the I will have, I think it's 2/5 mr squared. Yeah, it's 2/5. Now you also can have a rotation. Let's say, so this is when you have a solid sphere, and then this is expression. When you have a thin spherical shell, you have a different expression, and this is how many mr squared?
2/3.
It's a 2/3. Okay, so you can see that when you have a solid sphere and a spherical shell, they have a different, central mass. Central rotational inertia. Now let's see when you have this too. This is exactly the same cylinder. Okay, you have a solid cylinder, but this is rotating through. This is rotating through the central axis. So when it's rotating through the central axis, the I here is 1/2 mr squared. But then you can have an arrangement that you still have the same object, but now it's not rotating through the central axis. It's actually rotating through this central diameter. Okay, if it's rotating like this, your I here is actually this, huh? Okay, so 1/4 mr squared plus 1/12 ml squared. Okay, now the one that, the thin rod, which the example that I gave you, for the thin rod, if you are rotating through through a central mass, then that's 1/12 ml squared. So if you want to calculate, so in that case, what would be the new rotational inertia if it's rotating through the ends? We can quickly do the calculation because just based on this, you have right now. So now we have a 1/12 ml squared. So you have your I COM, that's 1/12 ml squared, right? So then the new I would just be 1/12 ml squared, and then plus what? The mass of the rod, and then the distance. So the distance here is 1/2 L, right? So you have, so that's times L/2 squared. So you can see that will be 1/12 plus 1/4 ml squared. Okay, so this is how you apply the parallel axis theorem when, and also the thin hoop. So all this just just to let you know that for different objects you will have a different rotational inertia. Okay, yes. Yeah, this has to be in SI unit, so it has to be in kilogram. Yeah. Okay, so I'm just going to do this. And why is it not? Okay. Just turning. All right, so for rotation, the other thing that we are interested is the torque. So that's what is torque? Before we talk about torque, that's think back. What is a force? What does a force do? What does a force do? It applies to an object, right? So when you apply the force to an object, what does it do to the object? It accelerates, right? Provided that the net force is not zero, right? So a force can accelerate an object. A non-zero force can accelerate an object. Now we're going to talk about torque. Torque is equivalent to force, except that it also involves where you apply the force. Okay, so what is torque? So before we actually talk about that, let's say when I want to rotate this. This is an object. I want to rotate it. So if I want to rotate this object, where would you apply the force? So there are many different places that you can apply force, right? I can apply here, it rotates. I can apply here, it rotates. I can apply here, does it rotate? No. I can apply here and it rotates the other way, right? And if you just see how easier, which location will be easier for me to rotate the object? Huh? The further points, right? The farthest, let's say this is your rotation axis, right? So this is your rotating axis. So if I apply this force, it's easy to rotate. And if I apply the hot wave through, it's not as easy. If I apply directly on the axis, it does not move at all, right? And then if I do this, I have to apply a greater force, for it to rotate. Okay, this is the same, same reason why the doorknob this is actually located at the, away from, this is your rotating axis. Just take, for example, this is a door. This is where the hinge, and then this is not rotating. But then the door, when you want to open it, you have to rotate this door, right? So this is why we put the bars right here instead of here or there, because apparently if you have this bar located right there, it won't do anything. When it's applied at the, when it's located away from that, you can open it, and then you'll find that if you place this right here, you'll have to, like double up the force in order to apply the same torque. Okay. So what exactly is a torque? So a torque has this expression. And we mentioned that it involves the concept of force. It also involves the radius where you apply the force. So the distance between where you apply force and the rotation axis also make a difference. So what is torque? Torque is equal to R cross F. So we have two vectors that are in vector product. So we have R cross F. So in that case, what is the magnitude of torque? So I draw the vector sign. What is the magnitude of torque? RF sine theta, right? And your theta is the angle between R and F, okay? Nothing, so if you have your R, if you have your F, that will be the angle between them. All right, what about direction? This is a vector product, which means that after the two vectors, after they do a vector product, you still get a vector. So what is the directions of torque? How would you determine the directions of torque? So let's say this is the bar, and you apply the force. You apply a force right here, and this is the distance up. What is the direction of torque? So what you want to do is that you want to draw extension of your R. So this is extension of R, and then whenever you have vector product, you have to use right-hand rules, right? So you point your fingers. Make sure you know how to use that because you're definitely going to use it. So point your fingers in the directions of the first vector, that's your R, and then sweep your finger toward the second vector, and that will be it. That's it. So your thumb gives you the directions of torque. So in that case, R cross F, your thumb gives you a pointing, is pointing out of the whiteboard. That is considered to be positive. So this force is producing a positive torque, because if you look at the fingers, your finger is counterclockwise rotation, so that's consistent with our definition of that being positive. Okay, so you have R cross F, and then you get a positive torque. You can have a force that is producing a negative torque. For example, let's say if you apply a force that's right here, and by the way, so for this R cross F, what will be the angle between them? This will be the angle between them. Okay? Now, if you flip your force is pointing now in this direction. What is your R cross F? What is the direction? Again, point your finger toward the first vector, sweep your finger toward the second vector, and your thumb now is pointing into the whiteboard, which means that this force produces a negative torque. Okay, so this is how you apply that. So this is as simple as that. It's just R cross F, and then in the book, which is this, you can it shows you that the components. So in other words, you can group them. This is like when you have R sine theta times force, which means that you're just finding the component of the radius that is perpendicular to the force. For example, what do I mean? So in other words, we're just using the force here. So if you can group them, so the magnitude is RF sine theta. So you group them, that's R sine theta and then times F. So your R, you can do the find the component. So this is force. If you draw the extension of the force, it's called the line of action, and then let's say this is your rotation axis. So you can find your projections of R. So in other words, your projection of R. So you treat that as a hypotenuse, and then so you have that's perpendicular to the force. So you have, this is what we call a right triangle, right? So this is hypotenuse, and this is your R that is perpendicular to the force. So this is basically equal to the radius that is component to the force and then times the force. Okay. So most of the time, I would just recommend you use this equation, that's just RF sine theta. But there are times it's kind of difficult to find the angle between them. Then you have to actually look at this to see what is the distance that is from the rotation axis to the force, and that is your R radius as well. Okay. So instead of using this R and then times the sine theta, you can just use the R that's perpendicular to the force and then times the force main to itself. Okay? Or you can group them that this is your R and then times F sine theta. When you do the F sine theta, which is equivalent to finding the force that is perpendicular to the radius, so you have the R and then F, and then I'm just going to say that perpendicular to the radius. For example, what do I mean? So in other words, this is your force, this is an extension of that. You can actually find the component here. This is the force that is perpendicular to the radius. You have that force that is in this direction, but you can see that this force does not provide, this component of force does not provide any torque because it's along the same direction as the radius. The only component that produces torque is this. Okay? So now, you have this is your F and then times sine theta, which is this, F sine theta and then times your R. And that makes sense because, let's say, if you want to rotate this, to open this, if you apply a force directly along the radius, this is your radius. Okay, if you apply a force directly at the radius, it does not produce any torque. It does not rotate at all. You have to apply force that is perpendicular to the radius in order to produce a non-zero torque. Okay. So same thing here. Along the axis, it does not produce torque. Only the one that's perpendicular to the radius will produce a torque. Also, if you apply force at the rotation axis, it does not produce a torque at all because there's no moment on. You have to have the distance. The force has to apply at the distance away from the rotation axis in order to produce a torque. If you have a force directly applied at that point, no torque is produced. Okay, so that's basically some of the things that you need to know. All right, so we look at this and we see that you have the torque that's equal to R cross F. How do we arrive at that equation? So take, for example, let's say we have a thin rod. If we have a thin rod, and this is our rotation axis, and let's say we have a thin rod, and then on the thin rod itself is massless, and then this object has mass m. So in that case, what will be the rotation inertia for that mass? And this is your R. What will be the rotation inertia of that object when this thin rod carries no mass and this object has a mass m and it's located r distance away from the rotation axis? So your I, by definition, that will be just, what is the definition of rotation inertia? Mass times radius squared, right? Okay, so that would just be mr squared. That's the rotation inertia. When you have a single particle with a mass m that's r distance away from the rotation axis, that is your mr squared for a single particle. Okay, not the extending object. And so let's say if we apply a force on this object and we let it rotate. Okay, and we know that this force, the tangential part of that force, and let's say this is theta, so that's your theta. So this force, the tangential part of the force, is going to produce a torque, as we mentioned. Because this force, let's say, let me draw a more dramatic way. So this is your force. The one that is along the axis does not produce any torque. The one that's perpendicular to the axis will produce a torque. Okay, so in other words, the tangential part of the force is going to produce acceleration on that particle mass m that we all know, right? And this is, of course, a tangential acceleration. So that force That force, if we multiply R on both sides, what we have here is R times F, right? So you have the R, and then that's equal to M, and then R times A, and then this one. So what do we have here? So what we have here is that on the left-hand side, we have our torque, because torque is equal to R cross F, and I just have the R times the tangential, the perpendicular component of the force. So on the left-hand side, you have your torque. On the right-hand side, what do we have here? So we have our mass, that's copied down. We have our R, that's from the multiplication of that. What about tangential acceleration if we want to use the angular, expressed in the angular form? How is it related to angular acceleration? So A is equal to something to do with alpha. How is it related to alpha? Wouldn't that be just that? Right? That's your A in relation to alpha. All right, so let's look at this. You have your M, you have your R squared, and you have your alpha. Ooh, all right, so what is mr squared? That's your rotation inertia. So we can see that your torque is equivalent to force. And your I is equivalent to your M is equivalent to your I, and your A is equivalent to your alpha. So you see that one-on-one correspondence, right? Your force is a linear concept. Your torque is for an object that's rotating. So when you have F equals ma, that's equal to torque equal to I alpha. Just like your K is 1/2 mv squared. If you don't know the expression for the rotation, don't worry. 1/2 I omega squared, because you know the one-on-one correspondence. M is equal to I, V is equal to omega, right? Exactly. So, for example, force can produce work. So in that case, this is for linear motion. This is work done by force that's moving an object from a distance d. What about when you have an object rotating through an angular displacement? How would you calculate work? So in that case, your F is replaced by torque. And then your D is replaced by, D is X, right? Theta, exactly. See? You don't even have to, derive everything. It's, once you learn this, you can just use it, okay? So let's go back to this. So what we found here is that your torque is equal to I alpha. And some people say that this is just the Newton's second law for rotation. So F equals ma, that's for linear motion. Torque equals I alpha. This is Newton's second law for rotation. And if you recall, there's another expression for force, which is when you're dealing with the linear momentum, that will be time rate of change, right? This is also what we call the Newton's second law, the time rate change of linear momentum. So you'll find that in linear motion, you have linear momentum. For rotation, you have also this equivalent concept, which is called the angular momentum. Okay, and we use L to indicate that's angular momentum, which is the subject for for tomorrow, I think. All right, so we can see that all this has correspondence, and all that also becomes very straightforward. Let's say power. Power is F dot V. For linear motion, when you have something that's rotating that produces power, how would you express that for rotation? So your force becomes torque, and your V becomes omega, exactly. Okay? All right. Any questions so far? No questions? All right, so that concludes chapter